Okay, Jim, would you want to say something to kick it off?
Well, certainly. Well, first of all, I want to thank you, Dashwan, and recognize you for coming up with this idea. Dashwan and I have collaborated on a few things, and he came up with the idea that, this question about how important knowledge of quantum mechanics is to quantum computing is something that we ought to do something about, and opening up a discussion for the community. So first of all, thank you, Dashwan, for coming up with this. I certainly didn't have the idea, and I would not have had the idea. Next, I want to thank our three speakers for being willing to lend their expertise to the discussion and presentation that we are about to all experience. All of these folks are very extraordinary researchers, and we couldn't think of better people to expose to the community to try to answer this question. So thank you, Ching, thank you, Steve, and thank you, John. And then finally, I want to acknowledge Max Liu, who has been our the sinew and muscle of getting this presentation done, because he's the person who's figured out the technology and how to make it work. And so thank you, Max, and we'll be eternally appreciative. So let me just say a few words, and then I'm going to turn it over to you, Dashan, and then we can actually start letting the real experts get into this discussion.
Right.
As many people know, quantum computing in some interesting and a bizarre way sort of got its start from Richard Feynman, because Richard Feynman at some point made a comment about all the computational power that apparently the universe uses in running its laws. And so this is sort of the first comment that many people ascribe as sort of the origin story for quantum computing. Now, it's tangential, but maybe there is something there, and maybe our experts will fill out that story in more detail, because after all, I'm just an amateur at this. I'm just talking about what I know. So Dashwan, I'm going to let you speak, and then let's let this rip.
Okay, great. Let me sort of give a few seconds why I thought about this. I have a very good friend, personal friend, who is sort of a big shot in computer science. And in the last 3 or 4 years, he kept on telling me he is trying to learn about quantum computing. And I said, well, that's great. Then about a year ago, he suddenly sent me an email saying that I finally figured out quantum computing is that I don't need to know quantum mechanics. And I said, that just sounds so strange, it just bothered me what he said. And of course, he's a computer science expert. I cannot debate with him on this issue. So finally, I just couldn't hold my curiosity and said, I got to organize something for the world to see. This is the first time where a field, physics, where quantum defines physics, computer, which defines computer science, which is a multi-dimensional field putting together, and someone in one field said, I don't need to know anything about the other, just sounds very strange to me. So I could be completely wrong today, what I said. And so I asked 3 experts who knows infinitely more than me to come and help illuminate this question, whether we need the quantum mechanical information in quantum computing. So we'll begin with Dr. Chang, because alphabetically he's ahead. So let's have Dr. Chang.
Okay, thanks, Dashan. Actually, I only can speak on my personal view. I'm actually starting from the quantum computing user. It's not the people to make the machine. Actually, I get it, in touch with the quantum computer. It's about 2017 when IBM, TC came to approach me. I was in National Taiwan University, TC Chang, and he said, hey, IBM are going to have the quantum computer online, and asked me, is that interesting to join and start to use the quantum computer online. frank to say, a lot of time I was quite skeptical and also curiosity. So I pay a visit to IBM, and they show me it's a real thing. So then we start to, join the program, IBM program. But as Dashan said, actually in the very beginning, at that time, I myself, I didn't decided I would get involved in this business. I just say, hey, come on, must be a good, interesting thing. It must be some people interested. So I signed agreement with IBM, and hopefully, I hope some other physicists or computer science, major were interesting to join this program. But turned out to be nobody interested on the 2016 or 17. Cannot find even one people want to do that. Even though I formed, visiting group of 6 professors actually from NTU to visit the Watson lab at that time. But however, since we already signed the agreement, I say, hey, come on. If nobody use, it's totally make no sense. So I decided I myself to get involved. So I asked all my students, you cannot do any other things. Only use the quantum computer to do your research. And what I still remember when I was in UC San Diego, the Cray 48 at that time just appeared, supercomputer. And my advisor asked me to use the Cray XMP48 to solve the problem, but he doesn't know anything. So I asked my student get involved. But turned out to be, after some time, they got familiar to that. And they really, show certain things. We can get something done. Of course, we do the benchmark in the very beginning, such as, we check what is IBM quantum computer can do, how many qubits are really entangled. And we check actually from the fundamental physics. So this is answer your question. You need to know, some physics, quantum physics, at least to do some benchmark in the very beginning, and then you need to know the quantum mechanics to understand all those quantum algorithms, like Shor algorithm, uh, other kind of the special algorithm use the quantum, science to implement those algorithms. Then later on, you can graduate to familiar all the things. Of course, actually, the GitHub also give a lot of help also for all the students. So later on, actually, we suggest the GitHub later on have the Chinese version. Actually, they also can use the Chinese. But anyway, so to answer your question, I think I have depends on in which way you use the quantum computing. Later on, then when all students get familiar with the fundamental things, then we try to find a real problem to do the proof of concept things. Then we need to know what kind of problem can solve. So we talk to all the people, then visit all the IBM Quantum Hub, and to understand what is the worldwide people try to solve the real proof of concept problem. Turn out to be they are more measured on the financial problem, material problem, drug problem, and also big data problem. And all those problems has a certain, after so many years, I think I have some comment on that because the quantum computer is have a lot of error. Right now, it's the Niski stage, noise intermediate scale, quantum computer stage. So they have a lot of error. So you need to find certain problem is tolerance those error. And turn out to be, big data problem, material problem, drug problem, and the financial problem. They are very, how do you say that? They are very error tolerance. You don't need to be very precisely, but just next to their best value is already enough. So actually, then you need to find other domain knowledge to work with you together, and then can find real problem to fit into the current stage of the quantum computer, then you can find their application side. So we spend a lot of effort to persuade the people, say, hey, come on, this is useful. So that's actually another reason I start to do the science popular talk to older people, because in the very beginning, actually, I think it cannot be done in a common language. But then you need to persuade other people. You need to make them believe quantum is not so hard. It's the future and is possible for them to use. Then you need to spend a lot of time to persuade them. And after so many years, I think also from the worldwide people gradually, appear and show a lot of evidence. So quite a lot of people right now believe is possible direction. So to answer your question is that is quantum mechanics or quantum science is necessary for quantum computing? I think it depends on which period are you in. If the quantum technology want to success to be a quantum revolution, I think that a lot of people need to get involved. Not only the people understand the quantum mechanics, such as, industrial revolution. Not so many people understand, mechanics or thermodynamics. If if everybody know that, if you want everybody know the mechanics and the thermodynamics, I think the industrial revolution will never appear. Actually, so it's a gradual emerging period, and quite a lot of people. It's a system integration, and how do you say that? The whole field need to fuse together. I think sooner or later, because of this, I think sooner or later, quantum and quantum engineering college will appear, just like the college of engineering, college of electronics show up, because this cannot be done only by the physicist. That's my general comment. Yeah, maybe that's it, and I will wait to see other things will come.
John,
So-
your turn now. John?
Oh, okay, thank you.
Yeah, go ahead.
So let me just answer the question first. And the answer is yes and no. It's a very good quantum answer.
Yes.
Okay, so let me explain why I say yes and no. And let me give you a first example of classical computing. And my point, if you're a computer scientist, you're writing algorithms and programming, do you have to know how the transistors in your cell phone or your computer work? No. Do you know electromagnetic theory? Because it's electrical circuits. No. So you don't need to know certain things for classical computing. And it's going to be a little bit that way for quantum computing too. But you have to understand why. Now, the reason why you can get away with your classical computer is that the classical hardware is so good that the abstract bit and the physical bit is the same thing. And you don't have to worry about how memory transfer works and all these things, and you can still use it. Now, eventually, a quantum computer, we're going to do the same thing. Okay, and in particular, physical qubits have errors in it, but eventually people will make a big enough quantum computer and a good enough quantum computer so that they're perfect. And these are called logical qubits. And when you have the logical qubits, then you can figure out how it works and do algorithms by, well, you can have some quantum mechanics, but the quantum mechanics on perfect logical qubits is actually really quite simple. okay? Much more simple than physical reality. So you're not going to take a physics quantum mechanics course to learn how to do that. And if you look at textbooks and the like, a lot of times they start out talking about logical qubits and how it works, and you can understand how it works. And that's great. And it's going to be fine. Now, I did want to mention one thing along this line. When I was at Google, we hired a Google software engineer. He was out in Boston and came out to Santa Barbara, and he had never taken quantum mechanics. And he learned quantum computing on his own by, reading textbooks or whatever. But he actually learned it in a very unique way, kind of developing some concepts by itself. And a perfect qubit, a logical qubit, allows you to do that. What was interesting about that is because he understood how perfect qubits, logical qubits worked in a different way, he actually broke a theorem that said what was the most efficient way to make something called a Toffoli gate, which you need for like building quantum adders and multipliers and things like that. And of course, the reason he broke it is he broke it is that he made a different assumption that physicists normally wouldn't make, because all the quantum mechanics textbooks to make those assumptions. He made a different assumption and got it. So learning about quantum mechanics in this different way is going to be I think, very powerful as people do that. Now, the real problem is that when you do physical qubits, they're not perfect. And if you want to understand how they work, you have to go and take your quantum mechanics textbook, because you have to understand quantum mechanics, circuit theory, maybe fabrication, all these things, okay, because they're imperfect. And if you want to understand their imperfects and make it better and do all those things, then you need the physics background to do that. Like, you don't need to know thermodynamics to drive your car, because all the thermodynamics is abstracted away because people have engineered it so well. So we definitely, if you want to work for a real system, you're going to have to know, the physics, quantum mechanics. Now, what's very interesting now is people, especially if they put their qubits online or they talk about the qubit system they built, where they've abstracted away quite a lot. There's something that people do that's very confusing in my mind. And that is they have physical qubits, which has errors, but they treat it as if it were a logical qubit. And sometimes they even say, well, you can get answers out of our quantum computer, without worrying about the errors. Okay. I call that kind of thinking magical qubits. That somehow that the real qubits, they have errors, but it doesn't matter. I don't agree with that, but it might be true in some cases. So that's what's confusing for people who are, looking at online systems or whatever. These are not magical qubits that have no errors. You can kind of get a sense of how it works by thinking in this simple-minded way, but you always have to go back and say, yeah, these are imperfect qubits. So I think that the nuances of the physical and logical and the fact that we're only looking at physical systems right now has to be understood by everyone. And, to do something useful, okay, you have to understand some of the limitations of it, but not everything. You can still abstract away quite a lot. But I'm going to say, to not understand the limitations and how to fit in a real algorithm, you have to understand that to some degree. But then, given enough time and we start making better qubits and logical qubits that don't have much errors, then we'll fortunately be in a regime where people can abstract it away, learn quantum mechanics and algorithms, and I think in a much simplified manner, because the qubit physics is quite a lot simpler than real physics of systems, and then then it'll be in the realm that you're hoping that it'll be, with these perfect qubits. That's all I have to say.
Very good.
Okay, so I guess I'm up next. And
Yep.
so I think I would completely agree with John with yes, no. Maybe I'll add maybe to that, to the original question. And as we've heard, it really comes back to how abstracted you are from the physical devices. And yes, computers, I would say 99% of computer scientists don't know how transistors work. And it's not particularly a problem for them. And, we're not at that stage for the quantum computer. But I think there is computer scientists, depending on what level they're working in, can work pretty abstractly. So I could go find dozens of paper on, say, error correction algorithms that really don't have physics in them. I mean, they're mathematics. So I've been teaching quantum mechanics to undergraduates on and off for the last couple of decades. And, 15 years ago, the sort of standard canonical way you teach quantum mechanics is you start with Schrodinger's equation and you solve the harmonic oscillator, you calculate position wave functions, Hermite polynomials, blah, blah, blah. Eventually you get to things like spin and maybe Dirac notation and the like. But as quantum information science has become more important, I've flipped the way I teach it. And so the way I teach quantum mechanics now is quantum mechanics is simply a set of postulates. And there's, depending on how you count, 5 or 6, things like measurement, Born rule, unitary evolution, Hilbert space. And then it's linear algebra. And you can do a lot of quantum computing science and not know how to solve Schrodinger's equation, and it won't harm you. And so I actually find this a much more interesting way to teach my physics majors. I mean, eventually we do get to Schrodinger's equation, but they start out much more conversant. I mean, they see Dirac notation the first day, basically, and it's linear algebra. In fact, we're developing a course at Maryland that's essentially quantum mechanics for computer scientists. And it's essentially this approach. It's sort of quantum mechanics is a set of postulates all associated with linear algebra, a set of rules, apply those rules, and you can do whatever you want to do with it. So is that understanding quantum mechanics? I would argue in a way, maybe it isn't. But nonetheless, if you look at where the field is at the moment, like I look at our computer science department, we have 3 faculty doing quantum computing in our computer science department. They all have physics PhDs. But I think that will change, right? As their students come out with CS degrees, they're going to start getting faculty positions. But it's a pretty unique time we are. I mean, it's actually kind of surprising how much progress we've made and also how slow it is, because, Shor's algorithm was developed in 1994. So we're 30 years in, which seems like a spectacularly long amount of time. But yet, on the other hand, if you look at, say, the technical progress in the last 10 years, both on the error correction side and the physical qubit side, there's been a tremendous amount of development. So I think there is now room for computer science students to really be working at the kind of higher level of abstraction, where they know quantum mechanics in this mindset of it's a set of rules for linear algebra and we'll apply those rules. And those can even apply to error correction and things. Yes, physical qubits have errors, and there's the distinction between physical and logical qubits, as John pointed out. But even there, I give you a model for what it does to my 2-level system. And again, it's linear algebra. So in the end, I think what any real successful program or company that's in this space needs is computer scientists and physicists who talk to one another. And I think John gave a good example for a person at Google. And as they talk to one another more, the physicists will learn computer science and the computer scientists will eventually pick up quantum mechanics at a relatively sophisticated level. So, the real answer is it depends. So I'll leave it at that.
Interesting. Interesting. A very good friend of mine, his son got admitted to one of the top computer science departments in the United States. I don't say which one. Okay, you just think of one of the top. And of course, he told me, he's a good friend of mine. Every time he comes back, we get together. And he said, you know, this word quantum computing is just constantly being mentioned in the department of computer science. And none of us understood quantum mechanics or had any course in quantum mechanics. And we sort of asked the department, namely the student asked the department, could we have a quantum mechanics course for us? And generally the answer was, well, we don't have anyone to teach it. And so if you really want to take quantum mechanics, it's not a requirement, but you have to go to the physics department to take the undergraduate quantum mechanics course. And being a good student, he took the initiative. He went to the physics department. And here he was with all the physics majors coming from all over the world, smartest physics students in the department, because I just can't compete with those guys. And the way they taught physics in the physics department for quantum mechanics, you know, unlike Steve was saying that you're specifically designing something for computer scientists, generally quantum mechanics course is just taught whatever way the faculty wants to teach it. And the students being physics majors probably had a lot of quantum mechanics knowledge already. So the faculty could just keep on jumping and jumping and jumping. And to the point where students in the physics department actually learn something because they know so much basics already. And so for someone coming from computer science, it was a big struggle. And so I think what all three of you must be saying is that while quantum mechanics may not be particular, the way we taught it in the physics department is precisely what computer science is needed, but it's still needed in the way that computer science scientists would need it. Am I right in this conclusion of the three of you?
Yeah, I think so. I mean, I come back to, you know, we teach Schrodinger's equation, you know, so it's partial differential equations.
Yeah.
Computer scientists don't need partial differential equations, right? I mean, that's irrelevant for computer science. They work in linear algebra, hopefully. So yeah, I mean, it's exactly right. That's why we're creating this course, because we have a number of CS students interested, but if they want to just go take our regular quantum mechanics course, there are all these prerequisites. It's part of our curriculum. It's just not the right thing for them. And I think you'll see more places do that.
If you wanted to teach a qubit kind of centered course, computer science centered course, it's so different than the way you think about physics that it would do it. And I would say there's, you know, the majority of the physics department don't think about it this way. And then you have to think about the continuity and you know, with other courses. I think you could teach, as Stephen mentioned, you could talk about quantum mechanics from a qubit perspective in the beginning and then go into the physics. I think it's possible, but since very few of the physics professors learned quantum mechanics that way, it would be an extremely difficult transition. So probably at this point, you need to have a separate course, you know, and find someone to do that. And then over time, you know, as people get more familiar and people get older, and then you could start to integrate it again. But
Yeah,
yes, it's a big problem.
Yeah, I think I agree John's comment. It's not easy to ask the existing professor, either in computer science or in physics department, to learn all the new stuff. Actually, they probably can over what they learn and what they are good at it. So maybe it will be great change. The future program, I think the interdisciplinary program appear. And of course, a lot of young students, when I give a talk outside, they ask me if they want to study the quantum engineering or quantum computing, what is the necessary course they need to learn during the university. I usually advise them, just as Steve said, linear algebra and plus quantum mechanics, a minimum quantum science, and of course, if you can have enough ability to do the double major, that will be best. Because actually for the next 5 or 10 years, probably still under the developing stage, no matter hardware or software engineering. So you need to have both knowledge, actually from the physics side, from the computer side. And so it's better to have a double major. Actually, they have one, very young, very promising young, quantum computing scientist actually recently graduated from Caltech, Xin Huang. His undergraduate is from our department. Actually, from our university. Actually, he's a double major, computer science and physics, and all get the best the score actually in each department. So then, right now, he actually in Caltech, and the graduate was how do you say that? He was got the Krauser Award and stay in California at Caltech as an assistant professor now. So if you want to do the pioneer one, you need to familiar with knowledge from both sides, and that actually gradually they will fuse together to have the new knowledge come out. I think they will figure out how to teach quantum mechanics from a different way, not only from the physicist way, and then things will change.
So kind of to expand upon that, if you want to be an experimentalist and build a quantum computer, you need to know quantum mechanics, okay, and that. But for our field of superconducting qubits, you need to know how to program, okay, and you need to take an electronic circuits, and you need to take a microwave engineering course. So the real issue here is you have to be much more broadly disciplined, and like you say, major or at least take courses in a wide variety of fields in order to understand that. And frankly, that's what makes this field very interesting, is that people come out of this fairly well-rounded in a variety of technologies, so that you have a large number of jobs you can do. Let's say you can't land a job in quantum computing, there's many things you can do with that knowledge. So I think it's a very good discipline for experimentalists, because you have to learn all these very interesting technologies.
Jim?
Yes, I'd like to jump in. The first thing I want to reflect on some comments that I heard from all three of our experts. And let me start with this issue about teaching old dogs new tricks, if I can put it that way. That was sort of in all three comments at one level or another. There are things I think that current faculty members who are used to teaching quantum mechanics can do that will help ease this transition. And this was sort of hinted at in a number of comments. I've actually taught quantum mechanics over the last couple of years while I was away from Maryland. And one of the things that we learned from this experience was precisely something that you said, John, Schrodinger equation. In fact, that I don't think that's the most effective way to teach what quantum theory is about. I was trained like all of us. We start with Schrodinger equation, but starting with the Stern-Gerlach experiment and looking what happens with electron spins and Hilbert spaces. These are the things that, as I have talked to my students over the last couple of years, come closest to what classically trained physicists already know that would allow them to make the transition to thinking about qubits. So I think there are things that we could do to more efficiently get these, like I said, old dogs to understand some new tricks. To think about the matrix model. You know, there are these two models of quantum mechanics. We all learned it. There was Schrodinger, and then there was Heisenberg. Well, it turns out that Heisenberg is closer, at least in my experience, to what you need in this new realm. And so I think one thing we could call on the physics community to do is to go back and rethink how we teach quantum mechanics, in view that even at its birth, there were these two ways to think about it. Heisenberg gets us immediately into linear algebra, for example. It gets us into Hilbert spaces. It gets us into thinking about how the observer dependence occurs in quantum mechanics in a quite sophisticated way. So that's one thing that I would like to hear comments from my experts about. And then the second thing is something that you said specifically, John. I would call that the overhyping of the magical qubits. This is something that worries me, because, you know, it is often the case that when an exciting new discovery is made, the researchers overhype it. And then what happens is there's the relaxation in the system when the results are not coming in as promised. And then you sort of turn off the people you want to support the growth. And so I'd like to also hear about any dangers that any of you see from the, like it's called, I call this phrase the overhyping of the magical qubit. So those are my two questions to our experts. And these are the last questions I'm going to ask rather.
Yeah, thank you. I wasn't quite sure how that would be accepted, but yeah, I think it's important to talk about it. And yeah, we always, as scientists, we always want to talk about what's great and what worked well and the like. But in fact, if you're building a quantum computer, which is a very complex object, more complex than the computers we're using here, it's a system engineering problem, and system engineering problems are limited by the defects in your system and the worst aspects of it. So that's something that I try to do all the time, is emphasize that. And we have to understand, what are the things that have to get fixed and what limit us, because that's what advances the field. And that's what I try to do in my talks, is to make sure people are thinking this way.
Yeah,
it's the fact that we're combining physics with engineering and physics with system engineering that makes it such an interesting topic. And that we, as physicists, we have to learn these other big concepts about, engineering in order to be successful in what we're doing. I just find that interesting, as for professional development, to learn, how other disciplines attack these problems.
yeah, I'm very much concerned about the hype problem. Part of the issue is the quantum computing industry grew during a period of virtually infinite VC funding. And the way you get VC funding is promising things. And a lot of things that have been promised are pretty unrealistic. And I mean, John's magical qubits are really systems that I could do with classical physics generally, because the reason they're magical is because you're ignoring the noise, and I could just simulate it classically. But, you can't go to someone to raise money and say, well, my qubits aren't great yet. Give me 10 years of development and fabrication, hard work, and eventually I'll get to something that is going to have economic relevance. So we've heard, and we still hear, all kinds of unrealistic claims. And so I find it frustrating because there's fascinating physics, there's fascinating engineering, there's fascinating system engineering, and it's somewhat that we put the cart where the cart, I guess, is billions of dollars of economic activity before the horse kind of thing. And it kind of perturbed the system in a way that hasn't necessarily been as healthy. I mean, maybe it's quieting down a bit more since VC funding has dried up some, and I think there's going to be perhaps a little shakeout of the community at some point. Hype is a big problem. Right?
Just to give a little color on that, I've just started a quantum computing company and been trying to raise funding for 2 years now. And we definitely see that problem.
Right.
And the thing is, if you go in and say, look, people are overhyping this. We've thought about it carefully. If you really do the good engineering, you can make a quantum computer. And, to me, that's the honest way to talk about it.
Right.
But for the VCs, it's like, well, if it's hard and it may not work because you say it's hard, why do I want to fund you? And but by the way, this other guy say it's really easy and great. And it's very hard to be honest. Okay. But I would say we were eventually successful by finding the right people. I think we can do it. I think we can be successful, but it's very much a narrow path to do that.
Yeah, my answer actually will be like this. I think John is the hardware expert. I think right now, frank to say, quite a lot of quantum computer provider already came out. We are organized one hardware quantum computer forum actually in Taiwan. There will become September 4th, actually a whole day forum. They have about 10 quantum computer company come to Taiwan to give a presentation and also discussion, such as IBM, Intel, NVIDIA, and Fujitsu, and Quantinuum, D-Rock. About 10 to 12 company will come. But frank to say, as a user, I use some of the quantum computer they provided, not only IBM. I do the benchmark. As Stephen and John just mentioned, if you really want the fault tolerance or error-free, actually, such as IBM craned, last year they craned more than 1,000 qubit, but the fully entangled one shot is very, very few, to say, very few. And also, if you operate, or if you put the gate operation, it's not so deep. They still need a lot of room to improve. That is true. So a lot of students use the real machine. They are so frustrated. So they will switch to simulator very soon. Because simulator right now use the classical computer can easily simulate to 30, more than 30. The best one, I think the threshold of the quantum computer and the classical computer is around the 70 or 80 fully connected fault tolerance quantum computer. That's still some time to go. But however, I think for last 5 years, those things really improved quite a lot. For example, I use the 5 qubit to do the benchmark on the Quantinuum. Their result is really just like the simulator. I don't know if more than 5 is that good or bad, but for 5 one, it's really just exactly like the simulator. We use the the program we publish on the paper, the same program we run the IBM computer, run on the Continuum, or even run on the Origin computer. And we do certain, benchmark on the different company. But turn out to be, the reason why I think the trap ion, suddenly goes off, because they probably do the entanglement and also the error control much better than the superconducting qubit in the current stage. However, the trap ion one, probably the size will be limited, so people still try to scale up problem. Probably is good for the supercomputing qubit. That actually John probably can comment on that. But I think the reason why most advanced, the big company still focus on the supercomputing qubit is because they have more possibility to scale up. But at the current stage, I think, frank to say, not all the result is much worse than the classical computer simulation. However, still it is good, The reason is that actually we really see the progress. If those progress can be keep the same momentum for the next 10 years, I think the things will change a lot.
Thank you. I'd like to remind all our participants that Max has requested that people should put their questions in the chat. Joshua, I don't know if you want to move on to the questions from some of our audience participants now, or do you want to continue the discussion with our experts?
I like to, at least before we go to that, I like to bring us back to our original question, and that is how much. Now, if I am a quantum computer user, whatever quantum computer is, I probably don't need to know quantum mechanics. But just like if I'm a computer engineer developing standard computer, I better know some semiconductor physics, which means that I better understand quantum mechanics. Now, quantum mechanics even quantum mechanics, this old subject, has changed quite a bit, at least in terms of new ideas of, just 2 years ago, quantum mechanics received Nobel Prizes. That's sort of strange, right? If you think about it, for winning Nobel Prizes in quantum mechanics. And those ideas have not seeped into quantum mechanics courses at all. And those ideas actually are very important. The two-level systems and so on are very important to, I presume, for the development of quantum computers. So in developing quantum computers, let's get back to that question in that form. Do I need to know quantum mechanics?
To develop a quantum computer,
yeah,
you do. I mean, although you do it in a big team, and there will be engineers who, know a little bit of that, and they mostly know their engineering discipline. But for the people who are running the project and coordinating everything, you absolutely have to know that.
And that is the problem, because I see that many departments now are called Department of Computer Science and Engineering. Now, if their engineering is developing old-fashioned computers, they can continue to do that. But if their new thing is to develop quantum computers, I doubt very much that these gigantic Department of Computer Science and Computer Engineering can even jump into the field to do it. Am I right or wrong?
So I would say, if I just use my computer science department as an example, the people doing quantum computing are all on the algorithm side, and that's fine. Yes, they know quantum mechanics because they were trained as physicists, but I could believe you could have computer scientists who don't really know quantum mechanics, but could still contribute say some new sophisticated error correction code. But if you talk engineering, yeah, no, then you have to know some physics for sure.
Yeah, because the department is called CS and E.
Yeah. Yeah, my department's just CS. So E is
Yeah.
somewhere.
So if you're going to be a CS and E,
Yes.
in other words, you're going to be developing computers, and in the most modern way would be quantum computers. Then to say that I don't need to know quantum mechanics seems to me it's a misnomer. I think there's just too many words that being used not carefully enough.
Now, the one interesting thing is if you're in studying semiconductor device physics, you have to know quantum mechanics to
Absolutely.
that. So there's advantage that the people in the device part of engineering, right? They're learning these basic subjects that allow them to understand what to do. And this happens when you look at quantum computing research groups. There are people from an engineering background that can contribute quite well.
I am not an expert on hardware, but if I think such a resistor, inductor, capacitor, equivalent circuit notation came out, all the engineering can design the circuitry without know any physics. So it depends on, can we have the effective circuitry on the quantum computer circuitry? If not possible, then in the future, probably they don't need to know any fundamental physics. I don't know, is this possible or not?
We kind of do that when we abstract away to a qubit, take a physical system and say, okay, let's just consider these two levels and what happens. And then you abstract away the qubit, and that's kind of like a circuit abstraction. You have to learn the rules. So that's done to some extent. But there's so many other rich phenomenon you have to deal with too, that you can't just roughly simplify it in this way.
So
you have to talk about how dissipation works and how energy loss works. And then that, that's a resistor. And in quantum mechanics, you have to get a little bit more sophisticated. But it's a good point. I mean, I think we have to work. Yeah, okay. So, think about it was 1910, okay, and you want to design some electrical circuits, but you know about Maxwell's equations, right? So what people developed in around this time is this, circuit equations and Kirchhoff's laws and other kind of simplifying concepts so that you can build things. And I think we're in that era now in quantum where we're trying to understand different ways to talk about it.
So unless, Dashwan, shall we move on to?
Yes, please.
Okay, so I've been monitoring the questions, and we have one question which starts out, for example, to use the quantum adiabatic computing model, what do you think needs to be studied? This is a question for to put to our experts.
So, in 2012, I and some other people really started looking at the D-Wave quantum computer because they were, coming out and claiming they can do things. At the time, we studied it, and we decided that it was not any more powerful than some classical systems to do that. Now, that's been 10 or 12 years. I don't know all the developments, but there is some hype that people say that it can do things. A lot of other people believe that it's not possible. And there's some basic physics that leads you to believe that there's not extra power from adiabatic quantum computing. But I'm not up on the latest thinking here, so I that's probably all I should say.
In terms of what should be studied, I think that would be an example where you need to know physics. There's no way, I think, to abstract an adiabatic quantum computer beyond physics. I mean, if we do gate models, we can abstract quite easily, but I don't see how you do that for adiabatic quantum computing. So if that's really a thing, you really have to know physics for sure. And like John, I haven't kept up with D-Wave and their current progress and everything, but it's
Yeah, and
something to think about for sure.
To understand if it works, you have to understand quantum tunneling.
Right.
And also you should think about multidimensional quantum tunneling.
Right.
And, you know, there's some physics there and people understand it. And, you know, that's why it's not quite clear that you can get a powerful computer from that. But again, you have to get very deep into physics to understand that. Yeah.
Okay, I'd like to move on to the next question unless, Ching, do you have something you want to add here before we move on?
Yes, please. Oh, and anything to add, Dr. Chang?
If they're talking about D-Wave, you know, it's some kind of the annealing problem. And it's very special kind of the problem. Actually, in physics, we call the, you know, in the quantum annealing problem, actually, we call the icing model in physics, but in the computer science, they call Kubo problem. And these two problems, actually, one is from mathematical way, a computer science way. The other is a physics way. But actually, they are mathematical form exactly the same. And D-Wave use the qubit to solve the problem. They can have the connectivity higher than a lot of number, but we also try that. I think not so much. But anyway, the other way actually is use a classical computer to simulate those problems. And such as Fujitsu use the digital annealer and to simulate those problems. And turn out to be, they can solve certain problems in a very efficient way. However, those problems actually, if you really want to use that, you need to convert your real problem or social problem or the real problem into the special mathematical form, such as icing model or Kubo problem. Then put those problems into the machine which you use. If you can do that, usually certain problem, you know, we compare with the SA problem or exhaustive measure. Some of the problem actually they really can solve much efficiency than other conventional measure. However, it's not every problem. So you cannot prove which kind of the problem is best. You only can try and error to see what kind of problem is best. And that actually is empirical way. And it's not easy to be put in the general form.
Thank you. Moving on to the next question from one of our participants. It's phrased, we're rightly discussing the issue of how to teach quantum mechanics for quantum computing. But I think we're forgetting that the quantum revolution is much broader than quantum computing and includes quantum sensors and even applications to the life sciences. The key developments were those by the AMO folks, also condensed matter. In the amazing way, they were able to manipulate quantum systems. Quantum computing is just one, obviously extremely important application. So I think an undergraduate education for non-physicists should still include some decent understanding of quantum mechanics so that they can pursue several avenues, not just quantum computing. So our expert's response to this statement, please.
Well, I'm a physicist, so everyone should learn physics.
Thank you, Chairman Rolston.
And I mean, you know, I do some work in quantum networking and things, so I do things beyond quantum computing as well. So I appreciate this comment.
Okay,
And it's interesting because as we start getting into, you know, say quantum sensors whose perhaps their first applications are going to be in the life sciences, right? You know, what we're really talking about here is interdisciplinary science. So does a biologist who wants to use a quantum sensor need to understand quantum mechanics? Does a quantum physicist developing quantum sensors need to understand biology? And probably the answer is yes for both of those. I think the place where computer science may be special is the ability to have layers of abstraction. And, you know, digital computing is the classic example where I know, Jim, you use computers, but you probably don't really know what the transistors are doing in your computer. But that's kind of a special technology, I think, in a way.
okay, unless one of our experts wants to weigh in.
John, do you have a comment?
No, I agree. And if for quantum sensors, you would have to learn quantum mechanics in the more conventional way to be useful. Learning about quantum information way would be helpful, but if you really want to understand what's going on with the sensors, that would be a more traditional course.
Dr. Chang, are you ready to move on?
Yeah, I think quantum sensor is a different approach like the qubit. Actually, qubit want to put them in a more persistent way to stay entangled as long as possible. So you can do a lot of gate operation to solve the problem. However, quantum sensor is similar like you use the opposite way. They are very sensitive to the environment. So you put a layer in entangled form. However, because they are sensitive to the environment, so they can sense the environment change very easily. So actually they do opposite way. However, I think they still need to understand the quantum mechanics and can make a very sensitive sensor.
Thank you. So the next question reads as follows. The book by Townsend is a great book that does include those topics that Dr. Feng was mentioning, and to which I actually alluded, starting with the Stern-Gerlach and the spin 1/2 systems. Like I said, I think it's very valuable for old dogs to try to teach from that book. It's such an experience. But this person says they really learned quantum mechanics in the last 10 years after learning and using that particular book and interacting closely with the AML folks. So this points to the importance of collaboration. And last but not least, there are some new books coming out. There's a new book by a colleague at Rice called Quantum Mechanics for Engineers of the Future. So this raised the question, what should we be doing as a field to hold up these new models? And do you think that this might, in fact, be something that even people are writing these books, but to the experts, would you look for more such books to be helpful to us? Is the question I'm going to translate from the original.
So yeah, when I'm teaching quantum mechanics, I don't use Townsend, but I use another book called McIntyre, which is a spins first book. It's very similar to Townsend in that way. So I mean, it used to be, Griffiths was the canonical undergraduate text, and Griffiths, the very first page says, here's Schrodinger's equation.
Right.
And, so there are now multiple choices that follow this more. Let's start with spin 1/2 systems. And so it's just a natural qubit, and it allows you to introduce Dirac notation, linear algebra from the beginning. And I think it's great that more books are being written. It's hard for me to envision wanting to write a textbook these days, given that I don't know any student who actually buys a textbook anymore. You're doing it for the service of the community, not for any remuneration.
This person also raised the issue, which I don't think we've touched on, which is the importance of group theory, because that's something I think is important. not teaching group theory as a mathematician would, because that's a whole nother issue, but group theory for the point of view of physicists trying to do quantum computing. Any responses to that in light of this question? And I think the answer is no. Okay, those are all the questions that I see in the chat. So unless some other comment comes up, Dashwan, I'm going to turn this back over to you.
I think that one of the important things we discussed today is that the general topic called quantum mechanics, the way it's taught may not be the right way at the moment for computer scientists. In some sense, the way that it's taught to physicists is also somewhat boring. You know, we teach Schrödinger equation, and then we teach a perturbation theory, and at some point we get to the Dirac's equation, one chapter, and that's it. But all the exciting things like entanglement and so on, which, by the way, entanglement, as I understand it, is quite important for quantum computing, is hardly ever mentioned in any of the textbooks. Now, maybe the new ones have done so, but I have not looked at them, so I plead ignorance here. So what is telling me from these three experts is that we need to really teach quantum mechanics to computer scientists, but not the way we taught in physics departments. We need to teach it to cater to their needs, but not to lose the fundamental ideas of what quantum mechanics is. We need to talk about, you know, we probably should at least have half a day of discussion of Schrödinger equation, and that's it. You know, don't do any more than is necessary. But the idea of how entanglement comes in and what are the important things, how entanglement could actually impact new engineering, quantum computing engineering, these are the things that probably should be discussed rather at length, so that you will capture their interest, the students' interest, so that they don't lose interest. And I don't know how you guys feel about this. Let me start with John.
Yeah, I think there can be alternative ways to describe this that can be very useful. And it's good that people are, you know, generating these textbooks and the like, so that people can learn it this way. I think that'll be very useful. And you know, it just takes time for these concepts to, you know, gel in a way that you know, can be a good course and to teach that. But yeah, I very much encourage people to think about this.
Dr. Chang?
Yeah, I think, you know, when we are undergraduate, the quantum mechanics, when you learn the quantum mechanics, they are inclined or try to train you to be a nuclear physicist or high energy physicist. So, you know, such as in all departments in National Taiwan University, used to be quantum mechanics are all these courses are all the privilege for the high energy physicists. So actually most the best undergraduate students also are interested to pursue as a astrophysics or quantum high energy physics after their undergraduate. But the graduate things change actually. Recently, right now, condensed matter physics can also have the privilege to join to offer the quantum mechanics courses. And they will emphasize on the different side. I think I agree with you. I think in the future, probably, if we want to, this one to be more diversified, the quantum computer to want to a lot of different curriculum people to involve, then the quantum mechanics book probably should be emphasized on different, chapter. May just as you say, entanglement should be more emphasized, and let people to understand more how to manipulate those things, how to use that. I think it's really need a certain time to do that.
Yep.
Yeah, I would just you made the comment about, the physics of 1910, and it's kind of funny. Our department and many physics departments teach a course called modern physics, where modern is defined as ending in about 1925. So when I teach quantum mechanics in the spin first way, I can do quantum information science in my first semester quantum mechanics course. We do Bell's inequality, EPR experiments. I introduce the circuit model. We, analyze the quantum teleportation circuit. And so it's actually a great opportunity, because rather than teaching students things that are all 100 years old, you can talk about things that are 10 years old or something. And it really is very engaging for the students, because they realize that they're not just learning a bunch of, old dead science kind of things.
Well, actually, I heard John today use the word entanglement. So that means it must mean very important to him in his development of the quantum computer, right? Am I right, John?
Oh, this is funny, because I call this the E word, and I try not to use the E word, because most of the time when people say entangle, they just mean the qubits are coupled and it's equivalent. Entanglement is a much more subtle and beautiful concept than that.
Absolutely.
So I apologize for using the E word improperly. Yeah, there's so many beautiful new concepts to talk about that have been developed in the last 20 years. It'll be good to start introducing those to this field, to standard undergraduate curriculum. But by the way, I took undergraduate, graduate quantum and enjoyed it. It's a very unusual physics, but I really got into quantum computing because I wanted to understand quantum mechanics, okay? Really understand it. And what I can say is, when you go ahead and you try to build a quantum computer, you really have a very deep understanding, because you can play with your quantum computer and get an answer and understand what's going on with that. And after a while, the quantum physics phenomenon is just like any other phenomenon you see, because you've been manipulating it yourself in these experiments. So that's what I find very interesting, is these are no longer strange concepts to us. They seem more natural and physical. Of course, it's an unusual phenomenon, but the simple direct experiments you can do really helps you understand what's going on here. And in some sense, maybe the best way to teach quantum mechanics is have people play with the quantum computer for a while, just like you play with, Legos or something, mechanical things. And then when you go ahead and take the course, it seems much more natural to you that it would behave that way. I mean, that would be a really nice way to really teach it.
Well, it sounds to me like, John, what you're describing is a quantum laboratory course.
Yeah.
We have another question, which goes, early motivation for building a quantum computer was to understand some hard physics problems using computers as an integral part of the phenomena. Surely this needs deeper understanding of quantum mechanics, but this would probably cater to a very limited set of users. Does overselling quantum tech prospects put the original Feynman's proposal at the backwater of exploration? And I remind you folks, that's where I started my comments this evening. So does it the Feynman question?
Computers first developed to to make a ballistic table. Okay, weren't, classical, and
Yes.
okay, people knew it would. So it started out, very simple, practical things that people were trying to simulate, and in nuclear explosions, whatever. But obviously, it expanded, and that's our hope for building a quantum computer, that will happen, and we just have to work hard to see if we can make that happen.
Yeah, I mean, Feynman's original proposal was essentially what we now would call quantum simulation, right? Solve hard quantum many-body problems. And that's still an active area of research. But I don't know whether John or Chang would agree, but if Shor's algorithm didn't exist, I'm not sure quantum computing in its current form would exist, and whether it would still just be people chasing quantum simulation and solving cute condensed matter physics problems.
Yeah, that's a very good question. I like that. It's really interesting to think
Yeah.
about, because that really changed the field and got people to think that you could solve mathematical problems, not just physics problems.
Right.
And that's what really advanced the field a lot.
Yeah, I agree. You need more, more advanced quantum computer to solve the general problem.
Yeah.
So we have a comment from one of our participants. It's about the experience of a physicist trying to get computer scientists in a collaborative educational modality, shall we call it. And the observation was that at the end of the day, only the physicists came actually to try to learn, and no one else. So this is a report of rather than a question, I guess it's a caution that we all should take in thinking about how to structure these things. I don't have any more questions that I can.
I'll just comment on that. It's a very interesting question. I think people in computer science and engineering are practically oriented, so that if you had a quantum computer that could, solve problems, and let's just say make money, okay, but solve real problems, then people would get really motivated to figure out what's going on and doing that. It's still a little bit of an academic exercise now. And we're moving towards that, but that's going to be, a big event for the field.
I apologize for my, I'm getting some video problems here, so I just switched over to my screensaver. So I apologize for not inflicting my appearance on everybody. As I said, those are the only questions that I see, unless Max sees some. Joshua, I'd like to turn the program back over to you.
Oh, thank you. I think one of the things that I listen very carefully to all the experts, is that we need some new thinking between and with physicists and computer scientists together. Physicists talk a language, computer science talks a different language. Sometimes these two languages don't seem to overlap much. And it is with more overlap that one can make progress in quantum computing. And I think that is true. The more we understand how each other's, not just intellectual thinking, but psychological thinking, if we can put that together, that would be a great thing. So since Stephen is the only one that can do that, because he's the chairman of one of the biggest physics departments in the world, not in the United States, he could initiate this with the big computer science department of the University of Maryland, and perhaps one of the future discussions we can have is for Stephen to find one or two people in the computer science and one or two people in the physics department to come together and see how to develop this curriculum of quantum mechanics for the new technology.
Well, we are working on it, maybe not at full bore, but it is
Well,
happening.
maybe you should be full board
Yeah,
now
exactly. No,
after today.
yep, exactly.
Yeah, yeah. Well, let me ask each of the experts to give a final comment now, since we are coming to an end. I'll start with John.
Yeah, okay. Thank you very much for the invitation. I enjoyed it and learned a lot. And you know, what I'm trying to do is build a working quantum computer that can solve problems. And I know many other people around the world are doing that. And I think if we can get to that milestone, start seeing some utility for quantum computers, then it'll really excite many people in the engineering, and will be highly motivated to, do the things you're talking about here.
Dr. Chang?
Yeah, I think I'm how to say, something like the optimistic person. I think sooner or later we will get a fault-tolerant quantum computer. Just how fast and how long we can get it. However, during this process, you need to motivate the general public, because you need the supporting from the general public. A lot of actually probably from the VC. Actually, my experience that most people is not interested on the knowledge of quantum. They actually are afraid of quantum. When you talk to them about quantum, usually 5 years ago in Taiwan, they would turn their face away. But recently, they really try to get a nose into the quantum, because they smell probably will make money. So actually, so you need to give them hope, and then can keep this road go a long way. And I think we need to let the general public know more about what is the possibility and what is the future of quantum, and that can keep the things go, steady and longer way.
Stephen?
Yeah, so to come back to our kind of original question, and let me broaden it beyond computer science, I think we're still in this very interesting phase where, the hardware is still being developed. Exactly what the platform is that may be the winner, if there is a winner, or there may be multiple winners, is still to be known. So I think we shouldn't lose track of the fact that it's an interdisciplinary topic. It's going to span computer science, physics, and engineering in all aspects. And so we have to learn to adapt our educational system. Universities, mine included, we're organized in departments. And so when you have these kinds of things that span departments, quite often it's hard to make much progress. So we really have to be, as you said, kind of forward thinking and working together across departments, across colleges, across disciplines.
Yeah, I mean, quantum computing really is sort of forcing two disciplines together. Physicists pride themselves as being the center for quantum mechanics. In fact, we are so centered on quantum mechanics, we don't even teach hydrodynamics very much in our departments. I maybe Maryland does, but generally people don't teach hydrodynamics, which is a very important area if you do nuclear astrophysics. You need to know those things. When I was doing nuclear astrophysics, I had to learn hydrodynamics on reading books that I never had a chance to take the course on. So I think quantum mechanics is sort of centered in our thinking. And for computer science, I think certainly quantum mechanics is not centered in their thinking. And now they're being forced together, these two ideas. It could be very exciting. It could mean the amalgamation of two totally disconnected fields working together. And so maybe Stephen, being the chairman of this huge department, has the opportunity to look for this future, which few other universities have the opportunities to do. But anyway, I think today we touched on many subjects where we may or may not have thought about it clearly. For example, someone mentioned today about linear algebra. Well, linear algebra, if you think about it, is nothing more than group theory. It's amazing when Alfred Lie developed group theory in the 19th centuries. He didn't know anything about physics, nor did he care about physics. And yet, everything we do now in physics, we touch on group theory. Group theoretical method was the underlying mathematics. And in fact, it's interesting. A well-known particle physicist told me that he was given this opportunity to teach quantum mechanics for the first year graduate school. He hadn't taught it for 20 years. So he looked at all the textbooks, and none of the textbooks talked anything about the interesting subjects. Maybe that will change soon. Anyway, he was also disappointed very much because as soon as he got into two-level systems, he talked about SU2, Lie algebra SU2. And the students looked blank at him because they had no idea what that meant. So he found out that every time he introduced any idea that has group theoretical related, he had to start from scratch to teach them. And he didn't go very far in the course, which so I think even for physics departments, maybe there are things that we need to think about also. But generally speaking, because quantum computing is so exciting, at least the possibility of making money, a lot of funding now depends on quantum computing. At least put the word quantum in it, and so I think that that will drive what we discussed today. One of the shortcomings today, although we have 3 absolutely outstanding speakers, we don't have a computer scientist in it. So I think that Jim, of course, have been pushing that we should make this a series of forums. So for the next few forums, perhaps we can also invite some open-minded computer scientists to join us in this discussion and see how we can work together. Well, that's all I have to say.
So Dashwan, let me make a correction.
Oh, okay.
John, do you need to go?
I need to go. Thank you very much.
Thank you.
Well, okay. All right, John.
Okay, but I want to correction. First of all, let me first thank our audience. Please, some of you have been kind enough to put comments in the chat about this program. Please give us the feedback on things that you think are very important if this forum series is to continue. We need to have you in our thought environment to figure out how to do this. This, as I said, this was actually Dashwan's idea. I simply joined him on this project. And by the way, he says I pushed for the series, but as I recall, it was already in his mindset. So I wanted to make sure that that was clear too, is that he's quite a dynamic leader, and I appreciate working with him. I want to thank the audience for bearing with us. We actually held our audience pretty well over the course of this hour-and-a-half long presentation. Thank you all for listening. And as I said, please give us feedback. And of course, I want to thank our experts, my chairman, Dr. Rolston, and also my colleague who reminded me we had met some years ago, Dr. Chang. It's very nice to see you again. And finally, for the audience, as a side note, I have been pushing my department to institute a group theory course, as Steve probably knows. So we're getting on board this thing also, because I also think that's a very important thing for us to do for our students who are thinking about getting into quantum science. So there's at least one.
I just put my email address in the chat. So if people want to give us feedback, feel free to send me emails.
Yep. And we've already got a suggestion about a computer scientist that I hope Max is capturing because I think he's monitoring the chat. So for me, that's all I have to say. Thank you, colleagues. I always enjoy listening and talking and interacting with bright physicists. You folks are very special in my life, so thank you. I'm going to sign off now.
Okay,
All right.
thank you.
Bye-bye.
Thanks for the
Bye-bye.
invitation.